Just a second. Okay. So I hope all of you have gone through this week's video. So we will start with the first topic, that is distribution automation. I think the screen is stuck on the previous one. Just give me a second. I think it will resolve. I think I'll just stop sharing and reshare once again. Yes. So first of all, first one is distribution automation. So basically, the earlier substation that we had, so it had manual control, manual monitoring, where people used to sit and manually monitor, and if anything is happening, then they take the control actions through telephonic conversations or going to the field and visiting to take the actions. So nowadays, what we are doing is we are automating all these tasks with the help of different communications softwares and everything. So we will go through one by one what are the components of this distribution automation. So first of all, you can see this is the data and control center, which is basically the master control station. So at this control station, all the information will be collected from the field, like from the substation, you can see. So from this substation where you have the transformer, breaker, switches, and power factor for power factor correction or for voltage correction, you have capacitor banks and rest all devices or components. And from there, the information will be collected through the with the help of your IEDs, which are your electronic intelligent electronic devices. So through these devices, the data will be collected, and then with the help of a data concentrator, these information or this data will be basically communicated to your master distribution automation master control station through the data concentrator. Then at the data distribution automation master control station, what will happen is it will using these data from the field, it will analyze or it will monitor the situation, and if it requires to take any control actions, so those will be communicated back. Control actions will be communicated to the substation. again through these data concentrators. Then what is the resolution here for distribution automation? Basically, the informations are basically at a resolution of 5 minutes. Then SCADA resolution is in seconds, maybe 5 to 30 seconds. So that is the resolution of the SCADA. And for the SCADA operation, you are having three major units here. Similarly, the master station, the RTUs or the remote terminal units, and the communication system. So similar to the distribution automation function, what will happen? We will see one by one that at the master station, what all components that you are having is firstly is the data acquisition server. Basically, data acquisition means to collect data. So it will collect the data, and if it is required, it may pre-process this data. So processing and preparing the data is done at the data acquisition server. And after that, you have the real-time data server, basically, which is collecting all the data in real time from the field. Then the historical data server is basically the data from the previous time intervals. So that was recorded and stored here in the historical data server. Then you have the application server. Basically, here it is a software which will process and do the computation for required for monitoring the. So this is the application server, and the operator workstation is basically where some basically operator is present, which is a human basically, which will take the decisions depending upon the results from the application server. So here again, this is the schematic diagram for the master station. Basically, you can see from the field devices, the data acquisition server will collect the data using communication systems, which can be wired or wireless that we have seen in the previous discussion. Then all these real-time historical data server are there. Then the application server will do the computation, and this operator workstation is basically a human which will take the decisions depending upon the application server. Then we have the remote terminal units or the RTUs, and here the major components are. Firstly, we have the central RTDB, then the physical input output devices, the data collection application, the data processing application, and lastly, the data translation application. So we can see from this schematic first what is happening. So, starting from this field equipment, the data is input to this physical IO application through these channels. First, basically digital or analog inputs, these are given. Then after that, the data is also connected through the intelligent electronic devices through communication channels to the data collection application. Then after collecting the data, you can do the data translation as we have seen here, and the translation and the data processing basically. So what here happens is basically maybe the analog to digital conversions. or maybe some arithmetic operation, arithmetic operations, or maybe some calibrations, or some that time stamping of the data, or some change of unit. So these all operations can be taken or done in the data processing and the data translation application. And then, like here, we have seen in the data translation application. So basically, the unit or the protocol of conversion can be take place, or you can filter the data or compress or aggregate the data, scaling and calibration. So all this function can be done in the data translation application. Then after that, these can be communicated back to the field devices. So this is the complete architecture of the SCADA system basically. So here starting from the input side, basically from the field, you get the pulse accumulator or pulse accumulator, which will basically accumulate the data over the time interval. Let's say whatever is your time interval, 1 minute or 2 minute. So these pulses will be accumulated over the 2 minute, and then the information of load or generation or whatever it is there. So it will be communicated to the uh, data acquisition data acquisition server, where maybe the data processing and the data translation will be take place, and this will be given to the master station, and then the master station will take the decision whether you have to close or open the circuit, or start or stop something, or change the set point values of something. And this information will be then communicated back to the field devices through the RTOs. Then next thing that we had was a smart meter. So again here similarly, the working of a smart meter is discussed. So firstly, the signal acquisition means basically what we are looking for, or what we are measuring here is fundamentally looking for voltage, current, and the phase angle. And then using these, we can further compute other electrical attributes such as your power or energy, power both active and reactive. So those all we can compute using these fundamental quantities. Then basically this signal conditioning, maybe some filters or something that are required. And then after that we convert them from the analog to digital quantity, so that we can communicate the smart meter data. Then next we had the various type of distributed energy resources, and we will study about solar and wind then in detail. So the various distributed energy resources that we have, first is the solar PV system, then we have wind turbines, then small scale biomass systems, combined heat and power systems, then energy storage systems, micro hydro systems, fuel cells, EVs, and demand response program. So let us first briefly discuss all these. So what do you mean by demand response programs? Anyone? What is the demand response? So basically, as it is evident from its name, demand response is nothing but the change in the demand with respect to some uh, events that are taking place in the system. So basically, when the demand is able to react to the system conditions, that means flexible. In simple words, flexible demand to support the system operation basically. So earlier, what was that the demand was not flexible. That means it was constant or it was not supporting the system operation. But now, with the help of demand response program, so let's say the frequency of the system is greater than 50 hertz. Then, if the frequency is greater than 50 hertz, so can you tell the relation between generation and demand? Which one is greater? Anyone? If the frequency is greater than 50 hertz, that means the total power generated is greater than the total load demand at that time. So to maintain the frequency at 50 hertz, to maintain frequency back to 50 hertz, we have two options. So the first one is either to decrease the generation or to increase the power demand. So, with the help of the demand response activities, earlier what it was only that the generation was changing to match the demand. But with the help of demand response program, the demand can also now change or vary to maintain the system frequency. And why it will do so? The why the demand will support system operation. It will be there if there are incentives. What do you mean by that incentives? Means if you pay the basically demand to increase its consumption during these intervals, basically incentives, then they will, if you give them money, basically they will support in the system operation. And similarly, when the frequency is less than 50 hertz, they can reduce their demand so that the frequency is brought back to 50 hertz. So that is demand response programs. Then we have a plug-in EVs. So how can this EV affect the power system operation? Anyone? Basically, the EV is using power, electrical power for charging purposes, right? Usually, what we do that basically you take your cars and then park it during the night hours or evening hours, and then take power from the grid to charge your vehicles. But similarly to the demand response activities, these EVs can also discharge or inject power back to the grid to support in the system operation. So basically, it is like coordinating their charging and discharging to support the system operation. So you can look at this EV as nothing but similar to a battery. So maybe one charging or discharging of one EV may not affect the bulk system operation, but when you have a of vehicles, fleet of vehicles means a large number of vehicles at the charging station. You can have multiple number of vehicles or at some parking lots of offices or apartments. So malls. So these all can act as a fleet of vehicles where combination of maybe hundreds of cars can be coordinated to assist the system operation. Then next is fuel cells. So these fuel cells can be your hydrogen fuel cells, where basically what you can do is whenever you are having excess renewables, like during the afternoon hours, whenever you have your peak of PV, then what will happen that suddenly there is a increase in injection to the system, so which may lead to issues of over voltage or over frequency. So instead of basically cutting off the power from the CV or basically curtailment of this PV power, to avoid that, what we can do, we can use them. And so this power from the renewables, we can convert them to hydrogen and then store it. And whenever there is a energy deficit in the system, then this hydrogen can be converted back to electricity with the help of these fuel cells. So that way, basically, the renewable curtailment is avoided. Then we have micro hydro systems, basically small hydro systems that are usually installed on the hills where the flow of the water is not very high, but it is at least sufficient to drive the small hydro turbines. Then energy storage systems that we have that similar to the operation of the EVs, their charging and discharging, we can basically coordinate to help to manage the system operation. And this energy storage systems are also of various types. For depending upon their application, you can install it whether you want it for high power applications or high energy type of applications, whether you want for storing the energy over a long period, like for months, or whether for shorter duration. So depending upon your application, there are a wide variety of energy storage chemistries that are available, and you can choose accordingly. Then you have combined heat and power systems. So basically, this CHP type of systems, they are not there in India, but in other countries where cold countries. So these heating systems are also present, and the heat network can be coordinated with the power network for their coordinated and smooth operations. Then small scale biomass systems, where we know that the energy from the yeah, small biomass type of system where the energy from your biomasses are converted to electrical energy. Then wind and solar. So this we will discuss in the next slides in detail. So what are the benefits of connecting this distributed energy resources? So firstly is the enhanced grid resilience. So why is that? Or what are the benefits of distributed energy resources? Any point that you want to add? So enhanced grid resilience means that by adding of this distributed energy resources, what is happening that in the event of grid disturbances or partial faults or complete failure, so they can assist and they can step up in the system operations and hence increase the resiliency of the grid. Then reduced energy losses. How can the energy losses be reduced? By the addition of this DERs. So these DERs are usually installed or are present in the distribution system. So if you remember the first lecture where we had the architecture of the electrical grid, so we have the generation system, then the transmission, and finally the distribution system. So the transfer of power from the generation to the distribution system, so there will be losses here. But what is happening now that in the distribution system, some DERs are being connected and the load are also present in the distribution system only. So basically what is happening that you don't have to transmit the power over long distances because you have the DERs at the point where already the loads are there. So that way the energy losses can be minimized. Then of course sustainability is a point. We know we have that we have the net zero target where we want that the emissions from the electrical grid is basically zero. So we are driving to that with the help of these DERs. Then peak load management. So similarly, as we discussed, that let's say during the peak load conditions, you don't have enough generation to meet the peak load. Then with the help of this demand response activities, what you can do is you can reduce the load during the peak hours and shift them to the non-peak hours. Like let's say during this hour is your peak period, and let's say this is your off peak period. So with the help of various incentives, what you can do that you can shift this load to off peak period and hence help in the peak load management. Then flexibility. What is meant by flexibility services is basically, you know that what will happen is the first requirement that you need in the electrical grid is that your generation is equal to your demand, and then flexibility services means which all services are helping you to basically maintain the system. So the first one is your this matching of generation with load. So this type of those services which help in matching the generation with load, so those are known as your balancing services. Then the other thing for smooth system operation is your the line flows. That is, the power flow in the line is within the limits. So these are congestion management. Then, of course, you have voltage. So this will be done through your reactive power. Basically, to maintain all these attributes, the system is requiring flexibility in the form of up or down regulation. Let me add a slide actually. Yes. So what usually happens is, so this flexibility services. So what is the need? So need is, as I had said, to maintain the system at a optimal or right operating condition. So for that, it was either matching the generation with demand or line flow or to maintain the voltage. And then basically how to do this, how to match with the generation with demand or line flow or voltage. So that is done with the help of up regulation service or down regulation service. So what are these up and down regulation services? So let's say earlier you had three generators to meet the system demand, and let's say it was at 200 megawatt, it was at 80 megawatt, it was at 0 megawatt. So this is your base case. So then we see that after some time with this schedule, let's say there is a line is getting overloaded. So what you need to do is you need to redispatch. these generators. So here the generators can either go regulation up or regulation down. So regulation up means increasing the generation from their base. So PG base plus your PG up. So this much amount of power that you increase, that is your up regulation service. And in down regulation, what will happen is when you decrease from your base quantity. So let's say with that, if we redispatch it to something like this, then again from both the schedule, the system load is being met, but now there is no congestion. So basically what happened to PG1, whether it is providing up regulation or down regulation, anyone? Earlier it was 200, now it is 180. This is down regulation, right? And what about PG2? It is already at its base only. And in PG3, earlier it was 0, now it is 20, so it is up regulation. So this was the example of congestion. So similarly, you can have different applications to maintain the voltage or to maintain the this power balance, and depending upon the need, the name of the service changes. So like your reserve services, your flexibility services, then to match the generation with demand in the real time services that we call as balancing services. So these are the different types of flexibility services. Then voltage and frequency regulation that we talked, and ancillary services is basically services that support the delivery of power. Then obviously grid decentralization, because earlier it was a centralized system where everything was in unidirectional from the conventional generator to the loads. But now with the help of this DRs, we have decentralized grid. We have renewables connected at the distribution side. Then avoided infrastructure cost. So this is meant that you now do not need power lines over long distance, because the demand can be met locally at the distribution system only. Energy independence and environmental benefits definitely. Next, we discuss about PV technology, photovoltaic. So we know that the main material that we use for the PV is silicon. So why we have chosen this material is basically it is abundantly available. It has higher efficiency compared to other materials in converting the energy from sun to electricity. Then stability and reliability, because the technology has matured for PV. So now it is a stable technology, it is highly reliable, and with this technology also we are able to increase the efficiency of the solar cell. Then scalability, you can easily, basically you can connect cells to form a solar panel, then panel you can convert into solar arrays. Then environmental compatibility. What are the disadvantages of this PV technology? So firstly, high initial cost, because you need to set up the panels, and the manufacturing of this panels is not at a lower cost. Then it is intermittent energy source, because the output depends upon solar energy, and solar energy, we know it will widely vary, that it is not fixed. So like maybe from morning 6 to evening 6, so you have something like this, and after that at the night again you have no solar output, and this peak may be at afternoon 12 or 1. But then again, it is not that every day this fixed amount of solar irradiance is there. It will depend upon the geography and all. So since we do not know how much it will generate, so again the matching of the generation with demand becomes difficult for this. Then again, since it is an intermittent energy source, so we need to install batteries with it, and this batteries or energy storage will add up to the cost. Then space requirement, huge space or huge land requirements are required for installation of these systems, and those are not readily available. Then challenge to the integration to the grid, because again these are intermittent in nature, and so sometimes they will create over voltage during the day, but again due to their absence at the night, under voltage problem during night due to the a variable injection of power from them. Then recycling and disposal, that is also headache. So let's say after 25 years or something like that, these PV panels, they will basically the lifetime will end. So after that, the disposal and their recycling is also an ongoing topic of research. Then obviously geographical limitation, because it will depend on which part of the earth you are located. As a tropical country, we are blessed with abundant energy source of solar. But if you go towards the pole, then again, they don't have that abundance of solar. So next is the generation of PV technology. I think the screen is stuck at once again. I need to reshare just for a second. Yeah. So we'll go through the generations of PV technology. So in the first generation, the material was your mono or polyamorous crystalline silicon, which very low efficiency of 13 to 22%, and it was very expensive to manufacture also. Then in the second generation, we had thin film type of amorphous silicon or your cadmium telluride materials were used for the PV cell, and their efficiency was 10 to 20%. The efficiency was decreased, but the cost was low, the production or installation cost, manufacturing cost. Then in the third junction, we have multi-junction solar cells or quantum dot solar cells. So they are under research and they have potential for higher efficiency and at lower cost. Then next we have grid connected. The grid connected versus standalone operation. So we'll see how the architecture changes in both this configuration. So for a grid connected system, it is simple. Yes. So here you have the PV, and this PV is basically injecting DC power, and then you have a inverter which is converting this PDC to PAC, and then it is injecting it into the distribution system to the loads. So in the absence of the PV, what will happen is this load will be met with the help of electrical utility, or this is the grid. So whenever your PV is greater than your P load, what will happen? The excess power injected to the grid. And whenever the power from PV is less than the load demand, then the deficit power is sought from the grid to meet the demand. That's why there is a bidirectional symbol here. So either you can inject or absorb from the grid depending upon your PV output. But what will happen in the standalone system, you have no grid. So in the absence of grid and with PV as an intermittent source, to manage the intermittency, we need to have a battery here. So battery will support the system operation through the charge controller. So you have the PV array, and this charge controller we'll see what are its function. So it will be coordinated with the battery, and it will control whether the battery will get charged or discharged. And then either if you have a DC load, then directly you can supply to the DC load, or if you have a AC load, then through the inverter you can supply the AC load. So the solar charge controller, so it will basically Monitor the health of the of the load, or basically the complete off-grid system. And if there are any issues, then it will basically disconnect those systems. So for over voltage or over current protection, for temperature compensation, because this storage have a problem of temperature also, that temperature need to be regulated. Then remote monitoring and control, system safety, battery protection, system efficiency, load management, basically to coordinate the charging and discharging of the battery. So all these are basically done at the solar charge controller. Then what is the impact of solar irradiance on the output of the PV cell? We'll see that. So this is the typical PV and IV characteristics curve of a solar cell. So you can see as the irradiance is increasing in this direction, irradiance increases. So the output power of the cell is also increasing. So this is the maximum output power that can be derived from the cell. And here in the current, you can see as the irradiance increases in this direction, the output current is also increasing. Increase of irradiance. The next is the impact of temperature change on the output. So here in this direction, as the temperature increases, so the output voltage is decreasing and the output current is increasing. Similarly, here as the temperature increases, the output power is decreased. Then why is the decrease in solar output with an increase in temperature? So it is basically due to the negative temperature coefficient of voltage and current. That means whenever there is an increase in temperature, what will happen is basically why there is flow of electricity. It is due to, that whenever the solar energy will be on the silicon cell, so electron and hole pairs are created, and due to this there will be a potential, and when you connect a circuit across this, the current flows. But whenever the temperature increases, what will happen is this electron and hole, they will recombine. So recombine means you have lesser number of free electrons to circulate the current basically, and that's why the with the increase in temperature, the solar output will decrease, and also there will be increased thermal loss with the increase in temperature. So all these factors contribute to the decrease in solar output with increase in temperature. Then this is the installed generation capacity for India. So if we can see, the total fossil fuel contributes to 56.4% of the energy mix, and of renewables we have 43.6%. And from the renewables, majorly we have 11% of hydro, and wind and solar are contributing to nearly 30%, where wind is 10% and solar is 16%. So highest amount of solar penetration is there, you can see. Then next we have wind. So what happens in a wind energy production from to electrical energy? So you have the input wind speed, then it will then rotate the blades of the turbine, and with the this will then in turn rotate the shaft, then which is the low speed. Basically, wind is given to the blades, which will rotate the low speed shaft. Then you have the gearbox, which will transform this mechanical energy. Basically, it is like a step up transformer for a mechanical system. So it will convert it into high speed shaft, and this high speed shaft will in turn rotate the prime mover of the generator to produce electricity. And then you have a transformer and you can inject this to the electrical grid. Then there are similar to various generation of solar cell, we have various type of wind turbine generator also. So the first one or type one was the conventional fixed speed type of induction generator. So you have some PF control capacitors here. So what are these PF control capacitor? Anyone? These we are basically using for power factor correction at the interconnection point. And then next we had the variable slip induction generators. By varying the rotor resistance, basically you can vary the speed. This was the type 2 type of wind generator. Then in the type 3, which is basically the DFIG, doubly fed induction generator. So here what you have, the power from the stator side, so this is the stator side, is fed back to the rotor, through the help of this converters. So you have two converter here. One is the rotor side converter and the other is the grid side converter. So the main aim of the grid side converter is to regulate the voltage here at the interconnection point, and the main aim of this rotor side converter is to manage the frequency here. Then in the type 4 type, you have the permanent magnet synchronous generators. So here what you have is the converter is basically directly connected here in the stator, and there is no feedback loop as there was in the DFIG. Mm. So that completes the discussion for the week one. Now we will discuss the some MCQ questions. So the first question here is the installed capacity of solar power in India. Someone say Rajesh says 9.01 gigawatt. Anyone else? Yes, it is 9.1 gigawatt. Then the second generation of solar cell were what type? A silicon wafer, advanced thin film, or none of the above? Oh, I think the screen is stuck. Oh, yes. Yes, the second generation was thin film type only. Yeah. So the next question is the conversion efficiency of a polycrystalline silicon solar cell is how much? 10 to 13. Actually, it is 11 to 14%. So these are all factual. Yeah. So the next question is mhm. Yes. So a PV array is having the open circuit voltage as 370 volt, short circuit current as 28 amps, and maximum power as 8 kilowatt. So what is the fill factor? Can you compute it? Fill factor, what is the formula for it? And then says 0.77. So fill factor is basically your maximum power, which is basically VMP into IMP divided by the open circuit voltage into short circuit current. So this translates to maximum power by VOC and ISC. So 8 kilowatt by 317 to 28. That is 0.77. And it will have no unit, right? Then what is the significance of series resistance in solar cell modeling. What does it represent? The load resistance, wire resistance, the top and rear contact resistance, or all of the above. Yes, it is top and rear contact resistance. Mm. Now, with the increase in solar irradiance level, the what will happen to VOC and I short circuit? Whether they will increase, decrease. ISC increase, which will remain constant. I think we saw it here. So we can see ISC increases and VOC also, if you see for the same amount, the VOC will also increase. So actually, both will increase. The next is which state is producing maximum wind energy in India? Gujarat. It is actually another coastal state, not Gujarat. It is Tamil Nadu from the south. The next is which type of generator is used in the wind turbine? DC, synchronous, DFIG, or none? Someone says DFIG. Yes, it is DFIG. So we see that it is mainly induction type of generators, either fixed speed induction generator, variable speed, or then we had DFIG, or recently then PMSG. Then how is the wind out power related to the speed of the wind? V cube. So the power is basically we had single half rho AV cube. So rho was basically energy density, A is the area swept by the blades, and V is the velocity of the wind. So there's V cube. What is the maximum efficiency of wind turbine? Someone says 59.3. Yes, actually, that is the Betz limit that we say that the efficiency of wind turbine cannot increase beyond 59.3%. Then what is the unit of irradiance, solar irradiance basically? Yes, you all are correct. It is watt per meter square. Basically, it is area. And what are the function of the solar charge controller? Yeah, it does. All of these protects from the overload from the battery for overcharging and block the reverse current path also. And what is the most expensive part of a PV system? Yes, it is actually the PV array, and after that, the next one is battery. Then for the wind turbine, the nacelle does not consist which of the following? It consists of all this: gearbox, high speed shaft, brake, low speed shaft, but it does not contain the wind vane. Then next is, why is the low speed shaft connected to the gearbox? Stability. Actually, it is not related to the stability of the wind turbine. It is basically to increase the rotation per minute because it is directly connected to the blades, which in turn are basically harnessing the wind energy. So they are nowhere related to stability or stress of the system. Then which of the following are not the part of a RTO? You remember RTO. So it is having the TDP, it is having data collection. What else was there? Also data translation is there, but this historical server is not there. What the historical server was a part of the master station. This actually completes this fixed discussion. So we are having time with us. So any query that you have regarding this week or previous week or anything related to this course, we can discuss. Any topic that you want to discuss. Have you submitted the week one assignment? I think the last date is 5th of Feb, right? Then, if you don't have any queries, I think we can close the session for today. So you can leave the meeting. We can continue. We will continue next week for week 3 discussion.